CAD Essentials. Before we start, go ahead and take the pre-survey for this course. Session 1, Spatial Visualization. Here are our learning objectives. In this session, you will learn what is CAD and what makes it useful, types of CAD techniques, spatial visualization, and to design your first part, Introduction to Onshape interface. What is CAD? CAD stands for Computer-Aided Design. CAD is used to model and engineer designs, allowing engineers to visualize, test fit, and explore how mechanisms function before prototyping or manufacturing. It is used in a vast variety of fields and industries, including automotive, aerospace, architectural design, product design, machine design, and several others. Why learn CAD? To make your design ideas come to life easy and quick, use CAD for your personal or class projects as 3D printing is increasingly becoming available in schools. It provides a way to create and test a working model and make multiple changes before final production. It's a great skill to learn, used by most industries for product design, whether you want to be an engineer, designer, surgeon, entrepreneur, or social worker. As you have seen how many people came forward to help during COVID-19 by 3D printing personal protective equipment for doctors, CAD can be used by anyone, not just engineers or designers. There are several types of CAD. There's 2D CAD, where you create geometric drawing or a sketch of a physical object. Most often, this is the first step to 3D modeling. And then there's the 2.5D or 3/4 view, where you create a graphical projection of 3D models on a plane to ease of display on computer, monitor, or paper. Interesting to note, traditional portraits contained in the National Portrait Gallery in London have been most frequently drawn in 3/4 view since the Renaissance period. Why? Think about how 3/4 projection gives both frontal and profile views, giving an idea about the depth or 3D-ness of a face. There is also 3D CAD, where you create three-dimensional realistic models, 3D wireframe and surface modeling, where you surface model to create a skeleton-like inner structure of the object being modeled, and a surface is added onto it later. And then there is solid modeling. The objective of solid modeling is to ensure that every surface is geometrically correct. For final production, this allows for automation of difficult engineering calculations made easier through CAD. Solid modeling is considered the most complex aspect to master in computer-aided design because it requires the CAD software to simulate the object from within and outside. The use of solid modeling techniques allows for the automation of several difficult engineering calculations that are carried out as a part of the design process. Simulation, planning, and verification of processes such as machining and assembly were one of the main catalysts for the development of solid modeling. Projections. How do we represent 3D objects on a plane? Take a cube. How would you draw it on paper? You can't say it's a cube just by drawing only the front, top, bottom, or side face. So you come up with a mental image of how the cube would look if you were to look from point A and draw what you see on a glass panel B. Shown in the first figure on the left is a perspective projection. There is also another category of projections called parallel projections, whereby the lines of projection to a plane are parallel to each other, as opposed to a perspective projection. All the other figures are parallel projections. Orthographic projection. Look at the projection of a cube on the red and gray planes and how the dashed lines of projection are at 90 degrees to these planes. An orthographic projection is a parallel projection whereby the lines of projection are perpendicular. This way, the shape of the sides of the cube remains squares. Isometric, dimetric, and trimetric views. Auxiliary views help in revealing more than one side of the object in a single drawing. Notice the differences in the position of the white dot and the length of 3 degrees. What do you find? What if we want to show many sides of the cube in one drawing? By means of auxiliary projections, image of an object as viewed from a skewed direction in order to reveal all three directions of space in one picture. Orthographic views. Where is the origin? What is the frame? Does it matter which axis is which? Be consistent. Break down the problem and look down the axis. What do you see? Approach it layer by layer. There are no hidden edges when drawing top, front, or right, but bottom, back, and left all have hidden edges, which we call negative. Again, go layer by layer, front to back. Here are some tips. Draw coordinates over the part and name them. Choose your view and draw the coordinates on the grid. Draw lines where there are edges, and hidden edges are shown using dotted lines. Solid lines trump dotted lines. The image on the left is rotated to the image on the right, as this image here is rotated to what? The answer is B. This image on the left is rotated to the image on the right, as this image here is rotated to the top, as shown here. These were some exercises for you guys to understand what orthographic views are. Now let's learn about some basics in CAD. Make a 2D sketch of your model. Use your knowledge of projections. Add custom features and extrude to create a 3D model from the sketch. And make a working model, assemble the parts, and add physical constraints if you need any. We will use Onshape to do this. It is free and available online to use without downloading any applications or software, so go ahead and make an account and check out the tutorials and videos to work on a more self-paced approach. Here are some tips if you want to use Onshape. Go ahead and pause here in the video or go to the slide. Here are a few more tips. The main takeaways of this session is that you should model around the origin, add relations, and then add dimensions. Fully constrain your sketch, and then use symmetry. Session 2, Onshape CAD Interface. We're going to design a peg block that you can use as a building block. Go ahead and pull up the slides or this video on the left part of your screen and the Onshape window on the right so that it's easier for you to follow through this tutorial. When you're on the Onshape website, go ahead and log in and create a new project and go into 2D sketch mode. Start by picking a plane. It doesn't matter which plane you pick, it's arbitrary, but the most sensible choice would probably be top plane. Add a center point rectangle at the origin. You always want to model about the origin. It'll help you use symmetry later. Constrain the rectangle. As you can see, we have 5 inches on one side and 2.54 centimeters times 4 on the other side. You can specify different units and even include some basic arithmetic operations in the dimension formula. Exit 2D sketch mode to 3D mode. Extrude the rectangle. Go ahead and choose the Extrude tool. It will ask you to select faces and sketch regions to extrude, and then you click on an enclosed area. Use the symmetric option within the extrusion tool to maintain origin at center. This is what it should look like. Go back into 2D sketch mode. Create a new sketch on top of the part. Not on the top plane, that would be embedded in the part and your sketch would be hard to see. Instead, select the top of the extrusion, we create new useful geometry on which to place our sketch. To create the holes and circles for our peg block, go ahead and right-click in the white space and select View Normal 2 to snap our view overhead. Place one circle in a corner and place another circle that's the exact same size directly opposite to it. Use equal constraints to match the circle's size. Drag or resize the circle's outline to show that both have the same size. Use the symmetric constraint to make the circles mirror across the front plane. Select the two circles first, and then the right plane, which is now projected into our sketch and looks like a vertical axis. We wouldn't have been able to do this so easily if we hadn't centered our starting rectangle about the origin. Drag the centers to show link. It should look something like this. Next, use the mirror tool. Select the right plane first and then the two circles, which would look like this. Now you want to exit 2D sketch mode and switch to 3D. Show that it defaults to extruding cylinders out of the rectangle first by extruding the holes. Reverse the direction, and if that doesn't work, now the cylinders are going to just come out the other side. So you have to select Remove Mode and Extrude. Rather than remembering that the block is 1 inch thick, use the Through All option. Now go back into 2D sketch mode and select a plane that is not the top plane. Start a corner rectangle from the origin. There are automatic constraints that are offered. If you hover over the origin, you'll find the coincidence constraint, and if you hover just above the origin, you'll find the vertical constraint. Draw an arbitrary rectangle that pokes out of the base. Do we want to extrude this material? No. It will not double the material, it will simply merge the parts, so there is no point. Exit the 2D sketch mode to 3D mode. Select the sketch, and then you must manually select Revolve Axis to select the revolve axis. Choose the rectangle side that is vertical to the origin. This is what it should look like. Now add fillets and chamfers. Why add them? They help with aesthetics, safety, they make corners more strong, and guides for posts or holes. And now we're done. Go ahead and explore what happens when you choose New instead of Add, as you can see in the screenshots here. You may also want to explore what happens when the sketch color as constraints are added. As you can see in this image, there's no color change. Circles have been reduced from 3 DOF, changeable up and down placement, changeable left and right placement, and changeable radius, to 2 DOF, changeable left or right placement, and changeable radius. Only the centers are black. Circles have been reduced from 2 DOF to 1 DOF. All lines are black, they're fully defined, and circles have been reduced from 1 DOF to 0 DOF. The 1 DOF has a changeable radius, but 0 DOF has nothing changeable. Session 3, Design a Face Shield. Today we will be designing a headband for a COVID face visor. We will use various features of Onshape to help us get a useful headband design, which can be 3D printed for actual use. You want to start by measuring the dimensions of your face. You can refer to the WikiHow on how to measure the dimensions. But you want the diameter of your head, and you will have to think about the dimensions you need to make a headband. The point of this project is to learn how to use multiple features in sketches, how to extrude different sections of the same sketch, adding fillet, and customizing appearance of part. The units and dimensions will be important. Choose a unit system appropriate for your design. Go to Document menu, select Workspace Units, and then millimeter, degree, or grams. Keep the exact measurements or dimensions of your design handy. For a better visual, this is what we are designing. Create a new Onshape document and name it as your name, your favorite color, and headband, and change the units to millimeters. Select the top plane, right-click, and view normal to plane. Now select Sketch from the toolbar and then select the top plane as the sketch plane. Select Center Point Arc from the toolbar and draw an arc of radius of about 85 millimeters as shown. Now, enter the distance between origin and endpoint of the arc as 85 millimeters. Select the two endpoints of the arc, select horizontal, and constrain the 2 points so that they fall in a straight horizontal line. Draw a vertical line through the origin and then using construction option, convert it to a dashed line. Draw construction lines and a point at 40 millimeters from the origin. Using these construction lines, draw another arc touching the two construction lines, as you can see in the picture. Now we will offset the solid lines using the Offset feature. Select the arc, then Offset. Select the arrow to change the offset direction. Make the offset distance as 1.5 millimeters for the lower arc. Now we will offset the upper arc. Delete the construction lines on the two sides. Select the upper arc, Offset, arrow pointing downwards, and then offset distance 2 millimeters. Offset the straight lines, then delete the construction lines on the two sides. Select the upper arc, Offset, arrow pointing downwards, and then offset a distance of 2 millimeters. Close the sketch by drawing horizontal lines at the ends of the straight lines as shown. Delete the construction lines on the two sides. Select the upper arc, Offset, arrow pointing downwards, and then offset a distance of 2 millimeters again. Trim the extra sections on both sides using the Trim feature. Make sure that the area between the lines is gray, indicating the figure has no holes and is closed completely. This will be useful in the Extrude feature. Draw rectangles using lines on the outer side of the band as shown in the figure. It will be easier to first mark out the points where you want to have the rectangles. Make use of dimensions to measure distances accurately. We are using lines to draw rectangles here for ease in drawing connected figures, but you can also try using the rectangle feature. Mirror the rectangles onto the other side. Rectangles with the same dimensions will appear on the other side. Mark a point 20 millimeters below the apex of the lower arc as shown, then draw a horizontal line through that point. Make it a construction line. Mark another point 95 millimeters from the center point on the line, and then use mirror to copy this on the other side. Mark a point on the apex of the upper arc, topmost point as shown. Such construction entities are often used to aid in drawing curves or arbitrary shapes. We will use 3-point arc to draw the third arc. Select start point, select end point, and lastly set the radius. Select the center point, which is highlighted in orange. We will draw another arc now using conic arc. For that, we will first draw 2 points and mirror them. Now, using the conic arc, select 2 endpoints of the arc and row as 0.5 millimeters. Note that the points do not seem to be on the arcs, but they still satisfy the coincident constraint. That's because the sketch has been zoomed in multiple times. Mirror the conic arc. Offset the arc. And then use construction for features. Draw these rectangular protrusions for hole punch for the visor. Use lines to draw these. Now that your sketch is complete, click on the green tick mark to finalize it. Now we will extrude our sketch one by one. First, the middle area of the sketch will be extruded. Choose Extrude from Toolbar, select New, select the region bounded by orange as shown in the figure, Symmetric, and then depth of 0.5 millimeters. Now extrude the band sections. Select Extrude, Add, select the region bounded by orange as shown in the figure, select Symmetric, and then depth of 15 millimeters, and then make sure the merge scope is part 1. Now extrude the band section. Select Extrude, Add, select the region bounded by orange as shown in the figure, select Symmetric, and select depth of 15 millimeters. Now extrude the small protrusions. Select Extrude, Add, select the region bounded by orange as shown, select Blind, and then a depth of 2 millimeters. Do the exact same step but make the depth 5 millimeters for the protrusions shown in orange. Now that our design is ready, we can refine it and add some color. Select Fillet, select 4 edges where you want to add the fillet, and select a radius of 0.75 millimeters. From the Parts drop-down, select All Parts. Right-click, select Edit Appearance, and then select the color of your choice. And with that, we finish. If you want to check out other cool CAD designs, go ahead and look through the slides for these links. Before you click off, please complete the post survey so we can get an idea of how to improve this course.